Okay, so this is where we stopped last time. We looked at certain guidelines for
Yes.
efficient modeling techniques, and we looked at one of the using that guideline, a particular design, how is it inefficient, and how to make it efficient as per the guidelines. Um, any questions on any of those slides? So,
No.
okay, so we'll move forward. Every language has something called a LRM, Language Reference Manual. That language reference manual is the structure based on which the language is defined. So Verilog also has a LRM. But LRM, each LRM for any language is in the Backus-Naur format. Okay, so what does that mean? Now, in the Backus-Naur format for Verilog, the if statement looks like this: if some condition is true, execute one or more statements, else execute one or more statements. This is what Verilog will look like if you type some simple example. In the Backus-Naur format in LRM, your case statement will look like this. There is an expression or a case variable, and if one value one of this variable, if that for value one you execute one or multiple statements. If this value is two or some other value, you execute some other statements. For the case statement, there is always a default statement. For default, you can execute one or more statements in case. So this will translate to a Verilog like this. Case Z and case X are also part of the language where case Z basically stands for your, in normal case, your values could be 0 and 1. In case Z, instead of case normal case here, Z, which is the tri-stated value, will also be considered. Or case when you have case X, Z and X considered as don't care. So basically, both cases they will consider it as don't care. So case Z and case X, though it's part of the language, is not synthesizable. Only the normal case statement is synthesizable. There is this expression, this conditional assignment, that conditional assignment statement that we have seen. If one particular expression is true, evaluate that. If it is true, then assign this value to the output, else assign the false value to the output. So it will look like this. So if you look at that, I mean, you can download the LRM from us. If you Google it, you'll find the LRM. There are for loops, there is while loops, repeat loops, etc. A lot of language. And based on this LRM, the actual Verilog is based on the LRM part of it. So, I mean, you don't need to, technically speaking, you don't need to look at the LRM. You just have to understand that there is a concept of LRM. Just like any language, Verilog also has a LRM. If you really want, you can look at that and see whether what kind of syntax is required. Okay.
Okay.
We have something called subroutines in Verilog. Subroutines, like any other language, are small programs or small sections of the programs which are defined separately, and we can call them on a repeated basis. Right? These are small routines, subroutines, or small routines or small functions, part of the program, which are in multiple times repeated. So to make the program more readable also and more structured also, we can define a subroutine for a part of the design which is repeatedly executed or repeatedly called for. So in such cases, it's called a subroutine. In Verilog, there are two types of subroutines: task and functions. So there are differences between task and functions. Yeah, so any programming language would have that task and subroutines basically. If you compare it to C language has functions and even structures if you have worked on C language. So Verilog has something called task and function. It can be part of the design hierarchy, especially the for task part of it. They are used in behavioral modeling. They are not part of structural modeling. They are used in behavioral modeling. And there are certain differences the way task and function works. A function can enable just another function. It cannot enable or call any other function, but it cannot call a task. A function always executes in zero simulation time, so there is no delay statements involved in functions. No timing control. No delay means also no timing control statements. We cannot have timing control statements like, for example, at posage clock. We cannot have that in a function. Function will at least have one input. It can have more than one input, but it will at least have one input, and it will always have only one output. So it will return only a single value. We cannot have more than one outputs coming out of the function. And there should at least be one input. It cannot be empty function with empty input arguments. At least one input and only one single output going from the function back to the main design. If you look at task, the task there are no such limitations. You can call other tasks or other functions. It may execute in non-zero simulation time. So we can have delay statements and other delay related activities involved in the task. So it can also contain timing control statements. For example, we can wait on passage of clock and execute certain logic inside the task. It can have any number of inputs and outputs or even bidirectional ports, zero or multiple. There are no limitations. It may or may not return any value. So there are no restrictions on tasks. So there are certain restrictions on functions. There are no such restrictions on task. Task is much more flexible to operate. But there are certain common factors for task and functions. Both task and function are part of the module. It is defined inside the module. It is not defined outside the module, but it is defined inside the module. If you remember, everything in Verilog is within the module. Since they are part of the module, they are local to the module. So the task and function defined in module number 1 cannot be accessed in module number 2. Okay, so that's how it works. It can have local variables, registers, but not nets and events. So both task and function can internally have a register defined, which will be a local variable for it or local signal for it. We cannot have wires or nets declared there inside a function or a task. We can only have registers. And it can have its own events, especially a task, not a function. Events in the sense at passage clock inside a task I can check for positive edge of clock, and on positive edge of clock I can, let's say, assign some value to a signal. I can do that. Both task and function can only contain behavioral statements. We cannot have module instantiations inside the function and task. Only behavioral description or behavioral statements can be part of task and function. Any module instances has to be outside the task, outside the function, even outside the always block. That is where we instantiate the module. So any other modules are instantiated directly inside the module, outside all these other procedural statements like always block, initial block, task, function. It should be outside that. A task and a function cannot contain initial or always statement. They are called from initial or always statements or other task and function. So there is no initial or always block inside a function or a task. But a initial or always block can actually call a task or a function. Other way around is allowed. Inside the always block, for example, I can call a task to execute certain logic. So task can be used for any, there are no limitations on task. Functions have certain limitations that it has to be purely combinatorial. It cannot, since there is no delay or no timing event involved, I cannot really model sequential circuits inside a function. It always executes in zero time and it provides exactly one output. Functions are typically used for conversions and common use calculations. So functions are used for any combinatorial circuits, basic gates, adders, subtractors, mux, demux, encoder, decoder. Any combinatorial circuit, you can use a function. If you are going to develop a sequential circuit, then you have to go for a task if it is not part of the always block. Do you want to note down any of this? Part of
Yeah. if you can go back to the functions and tasks
This
slides,
one?
I will note it down. Yes.
Yeah. Okay.
Yeah. Next slide, please. Next slide, please. Yeah, I'm done.
So, how does let's look at a couple of examples. This is how a task is defined. Task multiply. This is the name of the task. Each task can have its own input-output ports. Begin the task, begin this and then you have end tasks. This is how tasks are defined. If you look at functions, function 1 down to 0 test df. Test df, the name of the function is the value that we return back from the function. There should be at least one input to the function, and the name of the function is the value that we return back to the function. There is only one output. It can have one input or more than one input. So then begin the function, everything is inside begin and end, then end function. So this is how tasks and functions are defined. So there are certain keywords for task and functions. Keywords are task and end task for task. So any timing control, if you want to include any timing control construct, you have to use a task, not a function. It can have zero or more than one output arguments. So there are no limitations on input and output. It can be zero or more than zero inputs and outputs. This is the LRM syntax for a task. Task name, IO declarations, any register declarations, begin and end, in between begin and end, you can have more than one state in task. That is what we saw in the other slide. So this is the LRM syntax for the task. When you want to call a task, you can call a task by the task name. If it doesn't have any input output arguments, you just call the task by the task name. If it has any input outputs declared, then you have to map it to the local signals, the input outputs. So depending on the task declaration, you can call it with the required arguments. We'll see some examples. So IO declaration in module versus task. So task module also has input output, task also has input output. In both cases, the keywords used are input, output, and in-out. In-out is bidirectional ports. In modules, this represent ports connecting to the external signals. Means when you use it at a module level, those are like input-output ports connecting to other modules. So you can then at a top level you can instantiate both modules, module 1 and module 2, and they will be interconnected with each other using the input-output. When you have the task is part of the module. So any input and output for a task is within the task. So it's limited to the task. It's not outside. It doesn't go outside the module. It's within the module. Now this is an example of a task. How task is used. This is a module called operation. We don't have any input output ports at a module level. Parameter called delay, which is value 10. Then there are two registers A and B, capital A and capital B, which each of them is 16 bits. Then I have three registers, capital AB and AB or AB XOR. Each of them is 16 bits. Then I have this task declared. The task is called bitwise operation, bitwise underscore operation. The task has certain input outputs. First, the outputs are declared. AB, the small AB and small AB or small AB XOR is each of them is output 16 bits. Then there are two inputs, small a and small b. Each of them is 16 bits. This small AB and this small signals are different than the capital ones because Verilog is a case sensitive language. So what we are declaring here at a module level is capital. What we are declaring inside the task is small letters. You can use some other names also here. Here we are using the same name as this, but you can use some other names also here. Begin the task. Hash delay. Now delay is a parameter declared at a module level. Since this parameter was declared at a module level, it is accessible inside the task. Inside the task, inside the always block, wherever. The delay was declared at a module level, at a global level. So hash delay, AB and gets A and B. AB and, which is output, will be getting A and B. There are two inputs A and B. We AND them logically and the result will go to AB and output after some delay of 10 time units, whatever that is. AB OR is equal to A or B. There is no delay here. Inputs A and B are logically OR. Result will get assigned to AB or output. A XOR B. This operation will be performed and sent to AB XOR output. End and end task. Now this is a module level declaration. The initial block is at module level again. Begin the initial block. A is initialized to 16 tick H. So this is 16-bit hex value 0000. B is 16 tick H 0001. These are 16 bits. These are 16 bits. So A and B is initialized to 0 and 1 respectively. And we have a always block, always at A or B. The always block is sensitive to A and B signals, capital A and capital B here at a module level. Begin the always block. Inside the always block, I'm going to call this task bitwise operation. Now, when I call this task bitwise operation, I have to pass five arguments to it. Why five? Because it has three outputs and two inputs. So the input A and B will be mapped to capital A and B here, which are coming here. And the outputs coming from the task will get mapped to this capital AB and AB OR and AB XOR respectively. And always block end module. So what happens is inside the always block based on A and B inputs, these A and B inputs are passed to the task, which gets mapped to the inputs A and B here based on the location here. Capital A and B becomes small a and B inside the task. Then inside the task, we perform the logical and or logical and ORing and XORing operation and generate the required outputs. The required outputs get mapped to this capital signals, capital AB and AB or AB XOR signals. So this registers will, will reflect the outputs coming from the task, AB and AB or AB XOR capital. And the always block end module. Do you understand how task is declared and called for operation?
Yeah.
Right, so you can note down this example and we can go forward. So if you see the task here, it is using a delay statement. So there is a timing control statement involved, which is not part. If it was a function, it would not have been allowed. Since it was a task, it was allowed. And again, in functions, we cannot have more than one output. So in task, we can have more than one output. For a function, only one output is.
I'm done.
Okay. Next example of a task. Now we have a module called sequence. Again, there is no input outputs declared at a module level. There is a reg called clock. Now there are multiple tasks here. Task init sequence. In the task init sequence, all we are doing is assigning a clock equal to 0 in that. So it's something like an initial statement assigned for the clock within inside the task. There is a task called asymmetric sequence. Begin the task. Again, this task, first init sequence and this task, there are 0 input, 0 outputs. Here there are 0 input, 0 output. The clock, which is a register declared at module level, is directly manipulated inside the task. Task asymmetric sequence, begin the task. Hash 12, clock is equal to 0. Hash 5, clock is equal to 1. Hash 5, so after 10, 12 time units, clock equal to 0. After 5 time units, clock equal to 1. After another 3 time units, clock equal to 0. After 10 time units, clock equal to 1. So we are generating a clock signal basically, which is asymmetric in nature because the delays are different. So it's asymmetric in nature. End the task. End task. In the initial block, I call the init sequence task, which will initialize the clock to 0 value. In the always block, I will call the asymmetric sequence task. Now, if you notice here, init sequence and asymmetric sequence task are called with 0 arguments because there are no inputs and no outputs in both cases. So we are just calling the task name with no arguments here. In always block, we call the asymmetric sequence. It will generate a clock signal with this asymmetric delays involved. And always block end module. So we can have multiple tasks inside the module, which can then be called in the initial or always block. In this case, both tasks have 0 input, 0 output. There is a delay statement involved. Any of this is not possible with functions. Functions need at least one input. It will always have one output. I cannot write delay statements inside the function. Okay, any questions on this?
No.
You want to note this down?
Yeah. Yeah, I'm done.
Now functions, let's look at functions. The keywords are function and end function. It cannot have any timing control constructs. It will return a single value, so there will be a single output. And it will have at least one input. This is the LRM syntax for a function. Function name of the function, which will be the value returned back. You can have range or type. If it has more than one bits or the data type, you can declare it here. The input output declarations will happen here. Then begin the function and end the function. In between, you'll have multiple statements and then end function keyword. Function like task can be called with the function name and the required arguments. So it's something very similar to function in a C language. An internal implicit reg is declared inside the function with the same name. So the name of the function will be the value returned back by the function, and you don't have to declare a separate reg for that. Inside the function, if whatever function name is, a reg will be declared by that name automatically. You can assign an output value back to it, or you can assign a value which will be used as output back from the function. So return value is specified by setting that implicit range. You can have a range or type defined in the function. So the data type of the input can be defined. Data type of the output, sorry, can be defined, which is the function name. It can be, for example, integer or real, or you can have more than one bits. One bit. You can define all that. Let's look at a simple example. Module parity M. This is a module. Now inputs output at module level. Reg call address, which is 32 bits, which is initialized to 32 bit hex value 00000000. Then there is a reg call parity. This is a parity generator example using function. Function calculate parity. We have a function which has one input. Now calculate parity is the name of the function which will then be the output going back from the function. It is automatically a register declared by this name. Inside the function there is one input called address, which is 32 bits. Begin the function. Cal parity. Calculate parity is XOR. So this is a unary reduction XOR operator. Now 30 address is 32 bit. If you remember, parity generation is done using XOR operation or XOR logic, which we saw earlier. Now this is a unary reduction XOR operator. So 32 bits will be XORed with each other, right from 31 bit XORed with 30 bit, then the result XORed with 29 bit, the result XORed with 28 bit, so on and so forth, till we finally get 1 bit remaining value. That 1 bit value goes as calculate parity as the output of the function, which is single bit. End and end function. Then always at address ADDR, which is a registered at module level. It is always block is sensitive to ADDR. Begin the always block. Parity, which is a reg declared at module level. Parity is equal to calculate parity. I'm calling this function calculate parity and giving ADDR as a argument. ADDR is this signal which goes in as a argument to the function, which becomes address inside the function because that's the input value. And on that address 32-bit value, I'm going to calculate the parity and send back the parity value. The value returned from the function will be assigned to parity reg, which is at a module level. So parity will get the value returned back from the function. And then I will using dollar display. We'll see what this means. This is basically a display. We can message or display a message in the simulation console window using the system task. This is called a system task. Anything with a dollar sign is called a system task. So this will display a message in the simulation window. What will it display? Parity calculated is equal to %b parity. So this parity value will be displayed in a binary format. %b stands for binary. Parity calculated is equal to 0 or 1. That is what it will display. %b means it will be two values, 1 or 0. So this parity value, which was calculated by the function, will then get displayed in the simulation console and the always block in mode. So this is how function can be declared and function can be called inside the always block. Any questions?
No.
If you look at the function declaration, it will follow the certain rules for functions. It has at least one input. Yes, it is there. It will only send one output back, which is what it is doing. There are no timing control statements inside the function. We are not using any delays or anything of that sort, which is what the function doesn't allow. So XOR operation is a combinational logic. So that is what functions allow. Functions will allow you to implement combinational logic without any timing delay. Okay, so you can note down this slide of function example.
Okay. I'm done.
Okay, any questions on the function aspect?
Uh, no.
Okay, let's look at another example of a function. This is a shifting controllable shifter. Module shifter, no input outputs declared at a module level. Tick define. Tick define is called a compiler directive. We'll see what this is. This is basically define this like a parameter. We can use instead of parameter, you can use tick define for this. In this case, tick define left shift is 0, tick define right shift is 1. When we want to use left shift and right shift, we have to use tick left shift and tick right shift. When you declare it as a parameter, you can use it directly by that name. When you use define this constant with a tick define, you have to use this constant with a tick back tick here name wherever you want to do use that in the design. So tick define left shift is value 1 tick b 1 bit binary 0 tick define right shift is 1 bit binary 1. ADDR left address and right address, each of them is a register 32 bits. Control is a register single bit at a module level. Function shift 31 down to 0. So there is a function called shift, and the shift will be the value written back from the function, and this is 32-bit value. So the output of a function is a 32-bit value. There are two inputs to the function: address, which is 32 bits, control, which is single bit. Begin the function. Shift is equal to control equal to tick left shift question mark address left shifted by 1 else address right shifted by 1. So the way this works is this is a conditional operator inside the function. If control is equal to left shift, so we compare control with left shift value. Tick left shift. What is that? Is 0. So if control is 0, address will be left shifted. Address is the input at the function level. We will shift it left by one time, and that will get assigned to shift output 32 bits. Else, if control is not equal to left shift, means it's right shift. It is equal to 1. In that case, the input address will be right shifted by one time, and that value, right shifted value, will go to shift output 32 bits. End function. Initial block at a module level, initial begin ADDR at a module level, I assign it to some value 0000 FFFF. End. Always at ADDR, this is my always block sensitive to ADDR signal. Begin the always block. Left address here is equal to shift. So I'm calling the shift function twice. This function is called twice. Shift is equal to ADDR comma left shift. So I'm calling the function first time, giving ADDR and left shift as inputs. ADDR will go to address, left shift will become control signal. Then I'm calling the shift function second time, where the output here in this case second time will get assigned to right address. Shift address and tick right shift. So the functions are called twice. This function left shift is called twice. First case the output is assigned to left address, which is at the module level. Second time the output is assigned to right ADDR, which is again at a module level. End module. So this is how functions and tasks can be useful. We can call them more than one time. In this case, we called it two times. Okay.
Okay.
So you can always use a parameter here if you want, but this also is possible. Tick define is also allowed. The only difference is when you define it with a tick define, you have to use with a tick. The name of that constant has to be used with a tick, back tick here. Okay, so you can note down this example where a function can be declared and called twice.
Okay. Yeah, I'm done.
Done. Okay. So tasks and functions are used for behavioral modeling. The same purpose as we will use subroutines in software environment. Provides more readability and easier code management. So code management becomes easy for you when you are using subroutines which are called multiple times. They can be part of design hierarchy. So you can access a task or a function as a part of design hierarchy like a module. Tasks are actually more general than functions as we saw. There are no limitations on tasks, whereas functions has certain limitations. Functions, for example, can model purely combinational circuits, whereas task doesn't have any such limitation. And we saw that. So any questions related to task and function section?
No.
No? Okay. Time. Go 5-10 minutes more. So by behavioral modeling with Verilog, um, there are certain things now beyond timing control in behavioral modeling. So how we do that? So this is something how we can generate a free running clock. Always begin #10 clock equal to 1, #10 clock equal to 0. By doing this, we need a clock to be generated when we declare a test bench. So how do we generate a clock in Verilog using something like this? Always begin #10 clock equal to 1, #10 clock equal to 0. It is part of always block. So this is always executed. So the clock is continuously generated. This will generate a free running clock for me based on, we can change the delays, but it will generate a free running clock. Event control, in case of timing control, we have something called event control. So this was the example of delays in timing control, hash delays. Then similarly, we have event control. So delay execution until the event occurs. The event is the sensitivity list on the event is basically this event passage on the signal clock. Anytime there is a positive edge, logic 0 to logic 1 transition will be defined as passage. Always at passage clock, anytime there is a positive edge on clock, we can execute the always block. This is the event control part of timing control. Or we can have event control in case of just regular signals. Anytime any change in signal X, any change in signal Y, this always block will be triggered and execute the logic required for this. This is a timing control based on events. Both of this is a timing control based on delays. Okay.
Okay.
Hash delays directly are not allowed. They are not synthesizable. So this will not be part of the design. Uh, this part, always at passage clock or always at a particular signal, this is synthesizable. See, why is this not synthesizable hash delays? I cannot ask a chip to randomly wait for 5 minutes and do something, right? It is hardware. It is working on the board. Now, I cannot ask a chip to randomly wait for 5 minutes. I can wait for 5 minutes, but for that, I have to use the clock. So there is an onboard clock for the chip. So that if let's say this is going on FPGA, the FPGA is using is implemented on a board, is mounted on a board, and a board is generating a particular clock. Let's assume that clock is 25 megahertz. So that based on the 25 megahertz clock, if I want to generate a 5 minute delay, I have to build a counter, a timer basically. So depending on how many cycles I have to, or how many cycles I have to count based on 25 megahertz count, I will build a counter or a timer to ensure I get a 5 minute delay. Once that count is over, or once that timer is done, then based on that I can generate or execute some logic. I cannot just randomly ask the chip to wait for 10 minutes or 5 minutes. That is what we do for with hash delays. This is synthesizable because I can ask to, so at always at passage clock, my clock is 25 megahertz. I will build a counter here. The counter will go on a few thousand times, right, till I get 5 minutes. So few, not even few, multiple thousand times. So based on that, once that count is reached, then I can say that okay, now the 5 minute delay is over. Now I can execute certain logic based on that. That's how you can implement a 5 minute delay on the chip using something like this, but not with this. Because hardware doesn't understand this. Software, when you are working at a software level or simulation level, I can do this. It will use the internal that when we define the test benches in Verilog, we define the time scale, something called a time scale. Based on that time scale, it will understand. Let's assume the time scale is in nanoseconds. So hash 10 means I'm waiting for 10 nanoseconds. I can do it at a software simulation level, but I cannot do it at a hardware level. If I want to do it at a hardware level, I have to implement that kind of a delay or that kind of this thing using clocks, because clock is my timing reference on the hardware chip. Based on that timing reference, I am going to implement everything. There is no other timing reference on the chip. Only clock is the timing reference. So everything is with respect to clock. You got this point of delays on this.
Yes.
So clock is very important, as you can see, not only for event control and other things, but to make the design synchronous, your clock will be involved. To build any kind of delays or any kind of event control, your clock will be involved. Clock is a very important signal as far as design goes. Any questions on this slide?
No.
Okay. Then for behavioral code modeling, we have certain other syntax available. There's regular if then else conditions. If certain condition is true, execute one or more statement, else execute one or more statements as per the LRM of the language. We also have case statements where case there is a case variable, in this case opcode, and based on the values of the case variable we execute certain statements. For a case statement there is always a default. For example, now this opcode is 6 bit. Out of the 6-bit opcode, we are only worried about these two combinations 001, 0100, 001, 010. So this is 10 and this is 32 and 336 decimal, right? So these are two conditions of the opcode. The opcode is 6 bit, but when opcode is 10 and when opcode is 36, these are the only two conditions when I'm interested in performing some logic execution. In the other conditions, I don't really care. So what I do is I put this two condition, put my logic here, whatever I need to execute. The other conditions is I can say default means any other condition I don't have to include here. By default, in other condition, it will just say unknown opcode in that case or display. In this case, by displaying a message and end case. So this is a case statement which can be executed. Or we can use case Z or case X as is mentioned here, where I can say xx1 x1 x, for example. So or 001, or in other case I can just put in xxxxx. The rest of the conditions can be xx. But case Z and case X is not synthesizable. This particular piece of code is synthesizable. For two conditions, I am executing certain logic. For other conditions will go under default. In other conditions, by default, you do this. So we have a case statement, which is also part of behavioral model. We have repeat loops. We can repeat a loop X number of times. This is something very similar to for while and for loops. While loop, while a condition is true, execute certain logic. For loop, for the starting condition, ending condition, and increment or decrement the values. Execute the for loop. It's just a regular while loop and for loop. Repeat loops is something very similar to for loop, but it will repeat for X number of times based on certain variable. There are certain loops that are available in Verilog. So how do we? There are certain guidelines for simulation behavior. When modeling sequential logic, use non-blocking assignments. So we have seen that by now. For combinational statements, we can use blocking assignments, but for sequential logic, means for flip-flops registers, counters, we have to use non-blocking assignments. Since we cannot mix and match blocking and non-blocking assignment, we say that use non-blocking assignments everywhere. When modeling combinational logic, yeah, that's what I said. When modeling combinational logic with always block, you can technically use blocking assignments because there is no requirement for delays. But in case of sequential logic, we're going to mix sequential and combinational logic within the same always block. Use non-blocking assignments. That's a good guideline to remember that by default, just use non-blocking assignments. You cannot mix blocking and non-blocking assignment in the same always block. Another thing to notice is don't make assignments to the same variable from more than one always block. Okay, can you think about a reason why this condition is there? If you are assigning, let's say there is a reg called temp, and I'm assigning a value to temp in always block one and always block two. What means what will be the problem that will be created at your digital logic level?
The value that is assigned in the first always block will be carried to the next always block. So it's not a new register for second always block.
That's okay. It is not a new register, fine, but fine, then it will just override it, right?
But then if you're executing second always block, then it will wait for the first always block to execute and then the second always block will execute.
So how will the logic execute? Let's say you have to always block. How will the logic execute in that case?
So first the first always block is executed and then the second always block gets executed because it's the same variable for both always blocks.
Okay, forget the variable for now. Let's say you have to always block. Always block one and two. How will the logic get executed?
Based on the clock.
Right. But let's assume both has clock. Both are working with respect to passage of clock.
I'm not sure.
See, what is one thing that Verilog as a hardware language offers you that programming language don't offer you? There are a couple of things, but you can mention both. One is more important right now. You remember from our earlier slides, we saw the reason why we would need something like a Verilog or a hardware language, hardware description language. That programming language like C doesn't offer us that. That's why Verilog or VHDL was invented in the first place. Do you have your notes? Can we refer to your notes?
Yeah, but I don't recollect.
Okay, so I'll tell you that part and then you use that answer to think about this particular section. So two things that software languages doesn't offer that a hardware language offers you is timing control and concurrency. Right? For example, I cannot control my clock with a software programming language, not at a single clock level, single clock cycle level. Second thing is I cannot execute logic parallelly with respect to software programming languages. All my logic, let's take embedded C logic, everything will work sequentially. With Verilog or VHDL, which is used for hardware design, has to support hard concurrent execution of logic, which means parallel execution of logic. So always block 1, any logic inside always block 1 will be executing parallelly or concurrently with respect to always block 2. Inside always block 1 it is sequential, but always block 1 and always block 2 both will be executing parallelly with respect to each other, not sequential. So it will not be always block 1 then always block 2. It will be always block 1 and always block 2 at the same time. Inside always block 1 logic will be sequential as per the Verilog description. Inside always block 2 anything described in Verilog will be sequential. But both when you compare to each other it will be parallel execution. Okay.
Okay.
Now having revised that part, can you tell me why a variable cannot or signal cannot be assigned from more than one object? So this is
Why
a
a
rule in
variable? Can you
Verilog.
repeat the question?
So this is a rule in Verilog and it has to go back to digital logic fundamental. You want me to repeat the question?
Yeah.
Now there is a signal called temp. There is a reg called temp declared at the module level. Okay. And I'm trying to assign temp some value in always block 1 and I'm trying to assign temp some other value in always block 2. So let's say temp equal to 1 in always block 1, temp is equal to 0 in always block 2. What kind of problem will this create? Is this first of all a problem? If yes, what is the problem? What is the problem created? Now, okay, if you remember what we saw in digital logic design, any signal can have only one driver at a time. It cannot have multiple drivers at a time. It will generate something called a multiply driven signal in synthesis. Why? Because there are two drivers for temp signal. One driver is coming from always block 1, the other driver is coming from always block 2 at the same time. So if let's say temp is equal to 1 in always block 1 and temp is equal to 0 in always block 2, both always block. So logic of always block 1 and always block 2 is parallel with respect to each other. So parallelly I'm trying to send logic 1 on temp, at the same time I'm trying to send logic 0 on temp. That is going to create an X or an unknown condition on the temp signal, right? The synthesis tool won't understand whether to assign logic 1 to temp or logic 0 to temp, because at the same time logic 1 is driven on temp signal and logic 0 is driven on the temp signal. That is going to create problems for you. That's why if you're going to assign a value to temp, then it should be all logic with respect to temp assignment should be in one always block, not two different always block. Okay, that's what that line means. Don't make assignments to some variable from more than one always block. And don't, the last one is don't make assignment using hash zero delays. So hash zero delays are not, sometimes people try to use it as a kind of variable. So it's basically not synthesizable also. If you want delays, just use regular delays at a software simulation level, at a design level. Use a clock assignments, postage clock and neckage clock to generate delays. These are some of the design rules. Okay. Any questions on this slide?
No.
We will stop here today. Next class will be Wednesday, same time. If you find